Okay, good afternoon. A few things today. Let me pop this open and see, because I think we're getting close. Come on, Sumatra. There we go. All right. So last time we saw how to differentiate inverse trig functions, and we played around a little bit with that. Today, we're going to continue with the material from that is a consequence of the chain rule. That is, we're going to talk about derivatives of logarithm functions, and then we're going to start talking about related rates, both of which are consequences of the chain rule. Related rates, though, is our first step into really applying what we've learned. So today we're going to learn how to differentiate the natural log and other logarithm functions, and I'm going to show you some tricks that allow us to make easier the differentiation of some large, scary functions by using logarithms. And then Wednesday and Friday, and maybe a little bit today if there's time, I'll show you some related rates problems.
Going to make me feel any more beautiful.
Oh, I'm sorry, I could not hear that. Let me turn you up just a little bit. Could you repeat the question there? I thought I heard a question, maybe not. If you were asking a question, please just repeat it one more time. I've got you turned all the way up now. So today we're going to talk about derivatives of log functions. And in service to this, I'll do a brief review of logarithms. And then we're going to talk about what's called logarithmic differentiation. And if there's time, we'll do a little intro to related rates. Related rates, I gave a brief warning about last week, is one of the sections that students in this class often find challenging. So I would encourage you to put a little bit of extra love into those problems. But the first thing we're going to do today is talk about how to differentiate logarithm functions, which means we need to remind ourselves what logs are. So the base b logarithm is defined through the rule that y is equal to the base b log of x, means that b to the y is equal to x. Another way of saying this is that the function f of x equal log base b of x is the inverse to the function g of x equals b to the x. Okay. So this is the definition of the logarithm, but it's fairly terse, and you might not see exactly how to, for example, compute the base 3 log of 27 from this. So I want to look at an example or two and remind you how that goes. Of course, some special notation. The natural log of x, or ln of x, is just an abbreviation for the logarithm using the base e of x, where e, of course, is Euler's number, that 2.718. And log without any base is shorthand for the base 10 logarithm. Okay, so hopefully this is all review, but I know that it's very possible to forget some of these details. So let's, just for fun, compute the base 2 log of 8. Does anybody remember how to do this?
Isn't 2 like the base?
2 is the base. Yes, this is the base 2 logarithm of 8. Yeah.
Right. So 2 to the 8th power?
No, that we would just write as 2 to the 8. So let's do ourselves a favor. Let me call this y. And then we can use this characterization. So the base 2 log of 8 equals y means, just take the pieces and rearrange them in this exponential form. So this would be a logarithm form, and the equivalent exponential form would say 2 to the y equals 8. Good, yeah. So there are some true statements there. Yeah, the correct answer here is that the base 2 logarithm of 8 is equal to 3. For what reason? Because 2 to the 3 is equal to 8. i.e., the base 2 log of 8 is 3. So let's try another one. The base 3 log of 9. What is that? Good, this would be 2, because 3 raised to the 2 is 9. So you have to ask yourself, to what power must I raise the base in order to get the inside? So this would be 2. Let's try a few more. What's the natural log of e to the pi?
Pi.
Good, this is pi. Because remember here, ln is the same as the base e log. So we're asking, to what power must I raise e in order to get e to the pi? I'll do a few more. I want to look at a graph or two just to make sure we're feeling comfy. What is the base 5 log of 1 over 25? So remember what we need to say. We need to say, to what power must 5 be raised in order to get 1 over 25? Yeah, good. This is -2, because 5 raised to the -2 is 1 over 25. What about the base 2 log of the cube root of 2? To what power must I raise 2 in order to get the cube root of 2? Good, 1/3. Okay. So this is just evaluating logarithms. right? Just figuring out if I plug in some number to a log, how do I figure out what the log outputs? Graphs. And then some log properties. If the base of the logarithm is larger than 1, then its graph will look like this. And pretty much always the base of a logarithm is greater than 1. So here I'm going to graph you y equals log b of x. And I'm assuming that b is bigger than 1. You always have this vertical asymptote at x equals 0. The domain is always just the positive real numbers. You always go through this point, 1, 0. If b is out here, you will always go through the point b, 1. And you will also always go through the point 1 over b, -1. So if you want to graph the base 2 logarithm, the base 5 logarithm, the natural logarithm, they all look like this. Okay. My hope is that everybody remembers this from their algebra classes, but again, I know that's not necessarily the case. So we're just doing a quick review. There is no part of the graph over here because the domain is just the open interval 0 to infinity. They always dive down to -infinity as you approach 0 from the right. Right? In other words, the limit as x approaches 0 plus natural log of x, or any base logarithm of x, this is -infinity. And you could swap the base here. Most of the time, though, we just work with the natural log. Right? Most people don't bother messing around with other base logarithms. The natural log is really the only one you need. Last little thing of review here I want to touch on is properties of logarithms. The algebra properties. Because it is these algebra properties that will form the basis for all of the cool stuff we're going to do with logs. If you have a logarithm of any base with a product inside, that is the sum of the logarithms of the first thing and the second thing. So multiplication inside a log is the same as addition outside the log. And there are ways to get this wrong. If you have addition inside, you can't turn that into addition outside. If you have multiplication outside, you can't turn that into addition inside. This is the only way this works. This is our first important property. The second kind of important property here is what logarithms do to powers. So if you take the log of a power, like the base b log of x raised to the y, then that power can come down front. Remember, x to the y is x times x times x times x, y times. So the log of x to the y would be log x plus log x plus log x plus log x, y times, which is the same as y times the base b log of x. So powers inside can come down front as multiples. And then the last sort of property like this, which is really a consequence of the first two, is that division inside of a logarithm is the same as subtraction outside the logarithm. And all of these rules work regardless of the base. So this works for the natural log, as well as the base 2 log, as well as the common or base 10 log. But again, we'll pretty much always be using the natural log. So make sure you have these properties in your notes. And then let's take a look at how we differentiate the natural log function. Maybe one more property here. You may have heard of the change of base formula. We use this to get you the derivatives of other logarithms. This says if you have a base b logarithm and you want to turn it into some other base logarithm, say c, or the natural log, you can always write this as the base c log of x divided by the base c log of the old base. And one special case of this is that if you take an arbitrary base logarithm, you can always write it as the natural log of the inside over the natural log of the old base. This is the special case where I'm just using c equals e in this formula. Notice that there's only c's on the right-hand side, so you get to choose the base you want to convert into. You're given a base b logarithm, you're like, I don't like that base, I want to use the natural log. Okay. Or if you wanted to use the base 10 log, then you would just use c equals 10 here. All right, so this is all of our review on logarithms that we should need. I'll give just a second for anybody who's still writing. And then we're going to talk about the derivative of this function, the logarithm function. Please make sure you remember this graph. This is one of your fundamental graphs. It's a parent function. It's a graph that we need all the time. Okay. So differentiating the natural log. This is going to go very similar to how we cooked up the derivatives of inverse trig functions. Y equals ln x can be rewritten as e to the y equals x, using that definition. And now I can apply the ddx operator, and I get ddx of e to the y equals ddx of x. On the right-hand side, the derivative of x taken with respect to x is 1. And on the left-hand side, I differentiate implicitly. I get e to the y times y prime. which means that y prime is 1 over e to the y. But e to the y is x. So y prime is 1 over e to the y is the same as 1 over x. In other words, if f of x equals ln x, then f primed of x is 1 over x. Or another way to say this is that d dx of ln x is 1 over x. The derivative of the natural log of x is 1 over x. So this is something that you need to remember. You don't want to have to cook it up using this implicit differentiation trick every time you need to differentiate the natural log. It's not a hard thing to remember. So then the question becomes, how do I differentiate other base logarithms? I'm going to stop here for a minute and make sure everybody's comfy. Are there any questions about this? It is, yes, this is a derivative, just like, you know, the derivative of e to the x is e to the x, the derivative of sine x is cos x, the derivative of log x is 1 over x, and we should remember that. You'll hear me say log a lot for natural logarithm. Yeah, the derivative of ln x is 1 over x, and this is something we should commit to memory. Sorry, I've got a lot of weird lighting going on here today. Fix that. There we go. There we go. All right. So what about other base logarithms? Can we find the derivative of the base b logarithm in general? This is where your change of base formula comes in. Here, the original function f of x we can rewrite as the natural log of x over the natural log of b using the change of base formula. And this is the same as 1 over ln b times ln x. That's just some algebra, right? Dividing by 3 is the same as multiplying by 1/3. Dividing by ln b is the same as multiplying by 1 over ln b. So now if I take derivatives, f primed of x is d dx of 1 over ln b times ln x. And 1 over ln b is a constant. b, the base, is a constant, so the natural log of b is a constant. So this is 1 over ln b times d dx of ln x. And the derivative of ln x is 1 over x. So this is 1 over ln b times 1 over x. So the derivative of any other base logarithm is still 1 over x, but then you also have this constant 1 over ln b that comes along for the ride. Or if you want to write this in Leibniz notation, d dx of the base b log of x is 1 over ln b times 1 over x. Okay. So really it's the natural log that we use everywhere. Even when we're differentiating some other base logarithm, the trick is to turn it into a natural logarithm and then differentiate that. I want to take a second and help you understand this in terms of the graphs. Right, yeah, well, just like when you're differentiating 2 or 5x squared, the 5 pops out. When we're differentiating 1 over ln b times ln x, the 1 over ln b pops out. Yeah, because the natural log of b is a constant. So it's the same idea as differentiating a constant times any other function, right? That's one of the first differentiation rules we learned, is that constants pop out. Constant multiples pop out. So let's try to see this result in the context of the graph. Here's the graph of the natural log. All right, we've got our vertical asymptote. We're going through the point 1 comma 0. Over here at E, we're up there at 1. Look at these tangent lines. If I'm back here close to 0, the tangent line has a very steep positive slope. As I move out further, the slope of the tangent line decreases. And if I look right here at 1, the slope of the tangent line is 1. So if this is like 1/2, then the slope here is 2. If this is a x equals 1, then the slope here is 1. If I come out to x equals 2, the slope here is 1/2. And you notice the pattern with these slopes. They're following this rule. One divided by 1/2 is 2. 1 divided by 1 is 1. 1 divided by 2 is 1/2. So the fact that these slopes get shallower and shallower and shallower as you go out this way makes sense in the context of this derivative, because 1 over x gets smaller and smaller and smaller as you go out that way. In fact, in some slightly more advanced math classes, you define the natural log to be the function whose slope at every positive number x is 1 over x. That can be taken to be the definition of the natural log function. So just like last time, I'll add here, f prime of x is 1 over x. So we can see these two things together. Just like we did with the inverse trig functions, the next step is to learn how to apply all of our other differentiation rules with this function that we now know how to differentiate. So let's get some practice. Let's see if we can find the derivative of x squared times ln x. What rule am I going to need here?
Product rule.
Yeah, it's going to be a product rule thing, right? Because this is a product, x squared times ln x. If I want to differentiate the whole of x squared times ln x, first I'll differentiate the x squared and leave ln x alone. And then I'll add that to what I get by leaving x squared alone and differentiating ln x. The derivative of x squared is 2x, so I'll get 2x times ln x plus x squared times the derivative of ln x is 1 over x. And we can clean this up just a little bit. This is 2x ln x plus x squared times 1 over x. Oh, well, that's just x. Not too bad, right? For our next example, let's find f primed of x, where f of x is ln x over x. This time, instead of the product rule, I'm going to need the quotient rule. A quick question, can I cancel these x's? Yeah, no, right? For the same reason you can't cancel the x in sine x over x. This isn't multiplication. This is not ln times x. ln on its own doesn't make any sense. This is the natural log of x. This is function notation being divided by x. So I need the quotient rule. So f primed, the derivative of ln x over x, will be the bottom times the derivative of the top, minus the top times the derivative of the bottom, all over the bottom squared. That's x times the derivative of ln x is 1 over x minus ln x times the derivative of x is just 1, all over x squared. And then here, the x times 1 over x is just 1. So this is 1 minus ln x times 1 is just ln x, all over x squared. Could we, for example, find the location where f of x equals ln x over x has horizontal tangent lines? So maybe there's more than one. I'll say lines with a s in parentheses. Well, we just found f prime, that was the previous example. So I don't need to calculate that fresh. F primed here is just 1 minus ln x over x squared. Before I proceed with this, are there any questions about either of these derivatives that we did a second ago? Any question about that product rule or that quotient rule? Okay. If there are not any questions about where that derivative came from, then what do I need to do with this thing in order to find the location of any horizontal tangent lines?
Set it equal to 0.
Good. F of x has HTL, horizontal tangent lines, when f primed of x is equal to 0. F primed of x is, f primed of x is 1 minus ln x over, shit, did that paper really just tear? Over x squared. So I set this thing equal to 0. How do I solve that equation?
Can you replace ln of x with e up to the y?
No, because I don't have a y here, really. So we want to be comfortable solving log equations kind of as their own thing.
You can get rid of the x squared and
Yeah,
then,
this whole thing will be 0 when the top is 0. That's a good first step. So I'd have 1 minus ln x equals 0. What?
and then if you subtract 1, you get negative ln x is negative 1, which is ln x equals 1, and ln x equals 1 at x equals e.
Good. How do we go from ln x equals 1 to x equals e? What if I didn't just know that?
So ln of x is going to, in order to get 1, you've got to have a 1 in the power. So e to the 1, ln of e to the 1 is equal to 1.
That's true, and that's a good way to think of it. There's a little trick I like to teach here called exponentiation. You can exponentiate on both sides, meaning put both sides in the exponent of. So you exponentiate on both sides, and then e raised to the ln x is just x. So you get x equals e to the 1, or e. So this step here is called exponentiating base e. And it is a consequence of the first definition we looked at, that b raised to the log base b of x always simplifies to x, and also the base b log of b to the x always simplifies to x. Yeah, good, good. So this is definitely a pre-calc thing, the solving of this equation. And now we can conclude that f of x has a horizontal tangent line, just one of them, when x is equal to e. I might ask, what's the point on the graph? Where the tangent line is horizontal. How would I find the corresponding point on the graph? I know the x value. How do I find the y value? Yeah. I take this number and I plug it back into the original function, which was ln x over x. So this would be ln e over e. The natural log of e is 1. So this is 1 over e. Therefore, the point is e, comma, 1 over e. All righty. So this is how you differentiate the natural log, apply some of the differentiation rules to it. Product and quotient rules, those are good things. But what I'd really like to look at is the chain rule. Any questions on this example before I move away? Okay. Some more differentiation problems. Let's find ddt of the natural log of the cosine of t. This is going to involve the derivative of the log function and also the chain rule. So my outer function here is the natural log, and my inner function here is cosine t. So ddt of the natural log of the cosine of t, I should differentiate the outer function, leaving the inside alone. What is that going to look like? going to be 1 over what? It's tempting. Remember, we differentiate the outside, leaving the inside alone. So the inside here is cosine t. So rather than having 1 over t, I'm going to have 1 over cosine t. And then we multiply by the derivative of the inside. Yeah, so this is going to come out to the negative of tangent of t, because I'll have 1 over cos t times negative sine of t, which is, remember this sine t over 1, you can multiply straight across, you get negative sine t over cos t, which you can write as negative tangent of t. Cool stuff, right? Who would have thought that the natural log of cosine would have a derivative like tangent? It's kind of surprising, that connection between the trig functions and the log function. A neat rule, because sometimes folks do have a difficult time with this, applying the chain rule to the logarithm, because the derivative of the outer looks so weird when you leave the inside alone. A good rule is that if you're differentiating the natural log of some stuff, that will always come out to the derivative of the stuff divided by the stuff itself. So here we have the natural log of cosine differentiating to negative sine over cosine. This is the derivative of cosine divided by cosine itself. This is just the chain rule, right? That's really all it is. The more natural way to think of it in terms of the chain rule is it's 1 over u times u prime, but you can always move this u prime upstairs. So most people think of it like this. Let's try another one. What can I do here? How about, fuck it, let's do t squared minus 4t. So if I follow this rule, here u is t squared minus 4t, it'll be 2t minus 4 over t squared minus 4t. The derivative of the inside divided by the inside. Not too bad, right? Okay, bonus round. I got 2 problems for you here. Both can be thought of 2 different ways. How should I attack this problem? very good. If you first write this as the natural log of t to the 1/2, then you can use that rule for logarithms to bring the 1/2 down. Now that this is out front as a constant multiple, he pops out. And the derivative ddt of the natural log of t is just 1/t. That was easy. This is just 1/2t. If I didn't do that, and I tried to use the chain rule, that would work as well. I would get the square root of t primed over the square root of t. But this is much more complicated. The square root of t primed, okay, well that's t to the 1/2 primed. We'll write it like this. All over t to the 1/2. And then the derivative of t to the 1/2 upstairs is 1/2 t to the negative 1/2. And you see that this just doesn't look anywhere near as nice as this. You have to do quite a bit of algebra work to get this as simple as this. I can bring the 1/2 out and then write this as 1/t to the 1/2 times t to the 1/2, bringing the t to the negative 1/2 downstairs. And then and only then do I get my 1/2 times, well, t to the 1/2 plus t to the 1/2, that is t to the 1. So now I get my 1/2t, but it's much more work. And there's room to make mistakes. So if you're trying to differentiate a log of a power, use that log property to bring the power down front first. Then you can just treat it as a constant multiple, and life is much, much simpler. This, I would say, is the smarter way to go. Because I think from this line, pretty much everybody could have told me right away that the answer is 1/2t. Whereas here, from this line, it's not obvious. Differentiating t to the 1/2, there's room to make a mistake there. 1/2 minus 1, you might end up getting this power wrong. There's room to make a mistake here when you have to shuffle this negative power term downstairs. There's room to make a mistake here when you combine the two terms downstairs. So certainly, if you can do some algebra to simplify your logarithm function before differentiating, you should do that. Sorry, I'm trying to deal with this light that's coming in here. It's a warm day. Any questions on this fellow? All right, then with that in mind, how should I differentiate this?
Can't we simplify the natural log of e to t to just equal t?
Yeah. And ddt of t, what's that?
That's just 1.
Good. And this is perfect. And I think we would all agree that that's simpler than saying it's e to the t primed over e to the t. and then saying, okay, e to the t primed is e to the t, so that's e to the t over e to the t, and then canceling these and then saying 1. Neither is especially difficult. But again, by simplifying the log before we differentiate, all we had to do is differentiate t, which is about as easy as derivatives get. So I'm going to go fill up my water bottle here. I'll let you guys take a second to write these things down. If there are any questions on any of these examples, we'll address those when I come back. Oh boy. All right. Any questions on any of these 4 examples here? And it sounds like we're ready to start talking about what's called logarithmic differentiation. Logarithmic differentiation is a tool for differentiating functions that either cannot be differentiated directly or functions that you could differentiate directly, but you would need to use a shitload of product and quotient rule on. Let me give you an example. I could differentiate this using the quotient and chain and product rules, right? It's doable. It's not fun, but it's doable. If we use the quotient rule, we get that y prime is equal to low d high, that's the bottom, times the derivative of the top, minus the top, times the derivative of the bottom, all over the bottom squared. And then within each of these pieces, I would need to use other complicated rules. Like here, I would need to use the product rule, and not just once, but twice. Within each of those product rules is a little chain rule. And here, I would need to use the chain rule. Not nice at all, right? This is already looking kind of horrifying. I think we would all agree. So yeah, this sucks. and I'm too lazy. Mathematicians are lazy critters. We don't want to do shit that is unnecessarily complicated. We don't shy away from complicated things. But when confronted with something like this, we would prefer to find a more clever approach. So what if I took the log of both sides in the original function? So before I differentiate, I come back up to here and I take the natural log of both sides. Still no calculus being done. I'm just going to do a bunch of algebra. You remember in your pre-calculus class when there were all those problems like combine the logarithm or expand the logarithm as much as possible? This is why. Because if I take the log and then use the algebraic properties of the logarithm to expand this thing before I differentiate, I won't need a single quotient or product rule. I begin by writing the bottom as x squared plus 5 to the 1/2. And then I use my properties of logarithms. I expand this as much as I possibly can. So my first step, I have the natural log of a big fraction. So that is the natural log of the top minus the natural log of the bottom. I've already undone the need for the quotient rule. Next, I can bring this 1/2 power down front, and here I have a log of a product. So I can write this as ln x minus 1 plus ln x plus 1 plus ln x plus 3. The multiplication inside the log turning into addition outside the log, following the rule. And then I'll have minus, I bring this power down, minus 1/2 ln x squared plus 5. Can I expand this any further? Could I, for example, bring this power, this 2, down front? Or can I split this guy up as ln x squared plus ln 5?
You can't split it.
Cannot split it, right? Because it's not multiplication inside the log, it's addition. What about bringing the power down? Can I bring this 2 down front and cancel with the 1/2 or anything like that?
No.
It's tempting to say yes, but because it's not the case that everything inside here is being squared. If it was x plus 5 all in parentheses squared, then I could. But that's not what I have here. That's x squared plus 5. So if you could factor this, then you could expand it further. Or if you could write this as a chunk to a single power, then you could pop out the power. But as it is, this is as expanded as things can get. So you may want to revisit those log problems from your pre-calculus class where you just had to expand as far as possible or combine as far as possible. Yeah, this is it. So what I have right now is ln y is equal to all this stuff. I'll just write the ln y at each step here, right? So I have ln y equals all of this. I'm after y prime. So now I apply d dx to both sides. On the left-hand side, d dx of ln y. On the right-hand side, I have d dx of all this shit. And the magic is that the log took all the multiplication and division and turned it into addition and subtraction. So instead of needing some wild rules, I can differentiate each one of these on their own. They all require a tiny little bit of chain rule, but that's it. That's it. Much, much, much easier, right? What do I get on the left-hand side? What is d dx of ln y? Think about the rule I gave you on the previous page.
One over y?
Almost. There will be some.
Derivative of y over y.
I heard it. What was it?
Derivative of y over y.
Good. And what's the derivative of y?
1.
Y primed. So this will be y primed over y, or 1 over y times y primed if you prefer to write it that way, but most people would write it just as y primed over y, right? Like u primed over u. That was the rule. So y primed over y equals, now let's come through on the right. The derivative of ln x minus 1 is the derivative of the inside over the inside. So the bottom is going to be x minus 1. And the top, what's the derivative of x minus 1?
0.
1 minus 0, right? Or just 1?
Oh,
The x will differentiate to 1. The 1 differentiates to 0. The ln of x plus 1 will differentiate to something over x plus 1. The derivative of x plus 1 is also 1. The ln of x plus 3 will be x plus 3 primed over x plus 3. That's again 1 over x plus 3. Then I'll have this minus 1/2 times this last piece requires a little bit of actually something coming from the chain rule. We have x squared plus 5 downstairs. And then upstairs, I have the derivative of x squared plus 5, which is 2x. So I get that y primed over y is equal to all this stuff. So my last step is to just multiply both sides by y. In other words, this is like those implicit differentiation problems. We just need to solve for y prime now. Now here, this 2 and this 1/2 can cancel. And I just get minus x over x squared plus 5. And that's it, that's y primed. But remember, this didn't start as an implicit differentiation problem. I did have an explicit formula for y itself. So the very last thing I should do is take this y and plug in what it was originally. So let me shrink this back down. Is everybody comfy with these last few lines? Anybody need a minute to write? Okay. So we've got that y primed is y times this stuff. Last step, just go ahead and plug in what y was. So y primed is y, which is x minus 1, x plus 1, x plus 3, all over the square root of x squared plus 5 times 1 over x minus 1 plus 1 over x plus 1 plus 1 over x plus 3 minus x over x squared plus 5. And this is the same thing that you would have gotten from doing all that nasty quotient product and chain rule stuff. It looks a little bit different, but if you put it all together into one fraction with a common denominator, it would be the same thing. I don't know about you, but I know which one I would rather do. I would much rather differentiate logarithmically. And that's the name of that trick, where you take the log and then differentiate. That's called logarithmic differentiation. So what we just did is called logarithmic differentiation. It's a neat trick, right? Any questions about what we just did or how we did it? So here was the process. We took the natural log of both sides, expanded everything as much as possible, then we differentiated implicitly. Then we had to multiply both sides by y to get y primed alone. And then since we wanted an explicit formula for y primed, we just had to plug back in for y. Nothing too bad. So you need to be good with your log rules. You make any mistake in this stuff and the problem's ruined. You need to be good with the chain rule, right? Because each one of these little derivatives was a little chain rule problem. But differentiating logs is easy. It's just stuff primed over stuff. Right? It's nice. It's kind of the nicest of all the chain rule results. Not only is logarithmic differentiation useful for differentiating like big fractions, for some functions, it's the only way you can find a derivative. So let me see how we're doing for time here. Yeah, we're just about out of time. I want to do one more example. If you can hang around for 5 more minutes, I would appreciate it. If not, I understand. Just make sure you watch these last few minutes when the video goes up in a few hours later today. So one last example. Can we differentiate f of x equals x raised to the x? You may have never seen this function before. X to the x is a weird function. It's not a power function because it's not x to some constant power. The power is variable. Normally having a variable power would mean you're an exponential function, but oh, it's not a constant base either. So this is not like x to the p, so no power rule. And it's not like b to the x, so we can't use exponential rules. But we can use logarithmic differentiation. So we're going to use logarithmic differentiation. That's the game. I take the natural log of both sides. And I get that the natural log of f of x is equal to the natural log of x to the x. I can use the rule for logarithms, which says a log of a power can be the power times the log of that base. So in other words, this exponent comes down front. And now I differentiate implicitly on both sides. I do need a product rule here. I can't escape it, but it's not a bad product rule on the right. This is the derivative of x times ln x plus x times the derivative of ln x, which is ln x plus x times 1 over x, or ln x plus 1. And on the left-hand side, the derivative of the natural log of f of x is f primed of x over f of x. So finally, we can multiply both sides by f of x to get f primed of x equals f of x times ln x plus 1. Which means that f primed of x is f of x, which was x to the x, times ln x plus 1. So in your homework this week, there will be a handful of logarithmic differentiation problems. The first few will ask you to differentiate both ways, right? Like that big fraction we started with, differentiate using the quotient rule. Okay, now differentiate logarithmically to verify that you get the same thing either way. And then the last few problems will be problems like this, where the only way you can get the derivative is logarithmically. Once you get through the logarithmic differentiation stuff, you can stop for now, because the rest of it is going to be related rates. And related rates we'll begin talking about on Wednesday, okay? Any questions for me before we sign out? Easy peasy, yeah, it's not too bad. It's really not. There's nothing to be too afraid of here. Just be patient. Alrighty, then I'm gonna go ahead and end the meeting. I will see you guys next time. All right, keep working on that homework. Take care.